All right. So we'll start the last talk before lunch. And so we're very happy to have John Kleinberg, who's a professor at Cornell in computer science here. So John also works at broadly within Econ CS and now at the intersection of CS with lots of other fields, including fairness. And maybe the only thing I'll also add about John before letting him start, so he's also a former recipient of the predecessor to the Abacus Medal. So thank you.
All right, thanks very much. Yeah, it's a pleasure to get a chance to take part in this conference, and yeah, wonderful to get to celebrate Mark's work, and yeah, and thanks to the organizers for all the work setting this up. So, I guess it's interesting, of course, like the different talks. It's sort of, I feel like it's been surprisingly sort of diverse, the set of connections people have been able to draw to Mark's work, which I think is a reflection of just the incredible diversity of work that it spans. I was thinking back to, so I'm going to be talking in particular about some work that I've been doing, first with Senthil Mullainathan, a longtime co-author of mine, and then more recently some follow-up work with Fan Wei at Duke University, where we've been starting to understand the problem a bit better, trying to think about basic abstractions for the language generation problem. In other words, for the kind of problem that large language models are trying to solve. And we sort of started from Senthil and me thinking about, like, can we formalize what is it the large language model is trying to do in order to really try to understand some of the phenomena that we're seeing all around us. The work actually took us in directions that we didn't quite expect. And in a way, it reminded me of actually the first time I encountered Mark's work, which was about 20 years ago, namely computability theory over the reals, which was, I guess, the content of Mark's PhD thesis here at Toronto with Steve Cook. And in our own way, I myself, I remember seeing this and being sort of struck by how, there were still these fascinating questions that had a kind of computability flavor to them. And I myself was not working on those at the time, but this work that we've been doing actually on large language models, for reasons that we didn't expect, sort of steered us in the direction of what felt like sort of classical computability style arguments. And so that's been something that I'll hopefully share with you in this talk. I guess a more direct connection to Mark's work, of course, is just through communication as an organizing framework for many computational problems that, on their surface, as stated syntactically, don't always seem to immediately involve communication. And that's actually where I wanted to start with this work. The question of, can we base language generation or models language generation on some kind of minimal model of communication, right? That obviously, fundamentally, language generation is a communicative act. As we'll see, the sense in which I'm thinking about this is going to be fairly different from the way Christos talked about language this morning, though, of course, it'll be interesting to think about possible connections. But if I think about language generation, like what is a large language model trying to do? And I think about the communication involved, I guess, the obvious thing we think of it is, well, I'm communicating with it. I sit down at a prompt and I type some things and it answers back to me and we're communicating. I think actually the more productive analogy to communication it's going to turn out is a second one, which is that the communication is really sort of between the world and the language generation algorithm. Think of the world as providing training data, and the algorithm responds with valid utterances from the language which it's trying to learn. Okay, so the world just keeps showing it samples of valid language, and eventually the algorithm should start also uttering valid language, right? So it's not really necessarily a communication between you and the ChatGPT prompt. It's really a communication between this voracious algorithm trying to learn language and the world, which is outputting signals to it. Why is it potentially valuable to have something this simple as our picture? Well, because I think one thing we're trained to do as computer scientists is to sort of look for the abstraction barrier that sits between kind of what we're building and how people are using it, right? The so-called thin part of the hourglass, as a systems person might say, right? The idea that a huge amount of work is going on in the building of large language models, right? And it's, a sort of at a pace that's almost impossible to keep up with all of the arcana that are involved in getting state-of-the-art performance. And then a huge number of things are being built assuming language generation as a primitive. And normally in those kinds of situations, right, that we have the low-level implementation of cryptography, and we have all of the crypto and security protocols built on top of it, or we have the low-level implementation of packet routing on the internet and all the things, including the World Wide Web, that are built on top of that, right? That's often where we have a thin part of the hourglass. It's a little worrisome, you could say, that we have the infrastructure of large language models and all the stuff that's being built, and we don't necessarily have a really clear grasp of what is this thin barrier that sits between them. Like, what is this black box of language generation actually giving us that we can count on as we go to build applications? I think that's really a huge problem to think about. I'm not going to solve that problem here, but that's what I think motivated us to try making some progress on asking what is the minimal thing going on here, right? In the sense that, you can build a huge amount of crypto on the metaphor of Alice and Bob talking over a wire while somebody listens in. And just knowing that lets you build a whole lot of crypto protocols. I don't really know who the Alice and Bob are in large language models, but fundamentally that's a question about who's communicating with whom here. Okay, so that's the question we like to think about. Now, thinking of it as a communicative act, what LLMs are doing, I'm going to try to frame it so that it seems just straightforward that that should be a way to think about it. But it's not a given that that's how to think about it. And it's in fact not really how the field tends to think about it. It's of course a cliche and talks about large language models to at some point bring the LLM in as a character in the story. So I'll indulge in that cliche here. And of course, we could ask ChatGPT, what does it think it's doing? What problems does it think it's solving? And it gives kind of the canonical answer that, the primary objective, it would say is not to communicate with the user, to communicate with the world. It's to learn a distribution. Right? I mean, that's fundamentally how this tends to get conceived. That fundamentally the problem of what large language models are doing is building a very accurate distribution over all possible strings of words in this language of interest, be that English or Mandarin or French or C programs or Python programs, right? So that's kind of the canonical view, right? From a large collection of text, build a model that accurately assigns a conditional probability to every possible sequence of words. And once we have that, well, we can just generate likely utterances. But what's funny, and this is sort of where Sendel and I started, is that it was really our decision to put probability into this, right? That was our modeling choice. Probability is not really inherent to the original spec that this thing was trying to solve, right? If you want to think about it, the simplest way we could have stated the problem is simply design an algorithm that observes strings from an unknown language and eventually begins producing valid strings from the language that have never been seen before, right? Like if you wanted to say in the simplest language you could, what is it doing? Maybe it's that, right? So in this abstract formulation, the goal is to utter strings. A string, and here we're going to go back to the kind of classic Hopcroft and Ullman style, formalization of this. A string is just a sequence of symbols from a finite alphabet, and a language, in a, again, big departure from Christos' use of the word language. A language is just a set of strings. And actually, that departure is not accidental, because we'll find that you can actually do things with arbitrary sets of strings that are kind of more than you might have thought. Okay. Now, so for example, you could think of strings as English, I mean, we could say the symbols are English words, the string is an English sentence, the language is a set of valid English sentences. Of course, it's always a little hard to know exactly what's a valid English sentence. So if you want something that was completely well-defined, we could say the symbols are ASCII, and the strings are just all well-formed C programs, as in with this parse as a C program. Okay, and then the goal would be to watch a lot of C programs pass in front of you, not having any idea what this language is, and eventually begin outputting strings that are entirely, exclusively valid C programs, right? Could you do that? Okay, so we were thinking about this, and this seems too vague to be useful. Like, it's a very vague spec that we're giving here. But let's sit with, it feels a little uncomfortable thinking about something that vague, but let's sit with that uncomfortableness and just see what happens. So when Sundal was pushing us to like, oh, let's stick to this vague formulation, I was like, but this is way too hard to actually do anything. And in some sense, the reason why I believed that was a theorem that's now almost 60 years old called Gold's theorem, which is to imagine the learning of language as just a game played between an adversary and an algorithm. And it's really from Gold's theorem that I think we get this view of language as a communicative act, not between two speakers, but between a learner and the world, which produces signals, because that was Gold's picture. Gold's idea was, we think of language learning as a game played between an adversary and an algorithm, that the adversary thinks of a secret language, call it K, known to be produced by some representation, some finite size representation. So think like, by some conic tree grammar, some finite automaton, some space-bounded Turing machine, whatever it is you want. And because the representation is finite, there could only be a countable number of possible languages that the adversary could have in mind. Actually, we could throw away the representations and say even more simply, let's just say the adversary thinks of a countable list of languages as its possible candidates. It's going to pick one of those as its secret language, and then the algorithm has to guess it. What does it mean for us to agree on an arbitrary countable list of languages? Let's imagine that between you and me sits this box, and I can ask the box, is the string W in the language LI? And it will say yes or no, right? So a giant, doubly infinite 2D table that tells me which strings are which languages. And that box is all we're going to need for everything we're doing here. Okay. All right, so the adversary thinks of the secret language. What's the algorithm? Okay. And the adversary is going to reveal this to the algorithm kind of as training data, right? One string at a time. It's going to enumerate all the strings of K one by one in any order it wants. It can repeat strings, whatever, but it has to enumerate all the strings of K in some order. And in each step, the algorithm is going to guess what the language is. Okay, and the algorithm, so it's going to guess an index with the goal that that's the language. The algorithm wins the game if there's some step T star such that its guess is correct in every step after T star, right? So after some finite time, it's correct forever. And so strings come by. Now, this problem seems very difficult. Like when Mark Gold wrote this paper, he was trying to set up a problem that was like a super hard benchmark. He was not just thinking about computers. I mean, this was 1967. So to say the least, he did not have a massive web crawl sitting in front of him. He was actually thinking also about infant language learning. And he was sort of motivated by three stylized facts about infant language, like how a 6-month-old learns language, which also had, some of those had some echoes in the talk Christos gave this morning. Like one, yes, people make grammatical stumbles, but like the 6-month-old who can't really verbalize and just listening to their parents speak language, the parents don't generally speak gibberish. Like, yeah, they'll make some mistakes here and there, but fundamentally, the infant only sees positive examples. Also, the 6-month-old can't verbalize, right? So it might be guessing what the language is, but it can't ask if its guess is correct. Nor can it even output strings and get feedback because it can't verbalize. I mean, sure, eventually the 6-month-old becomes an 18-month-old who now does start to verbalize, and then the nature of the learning process changes. But the 6-month-old is making a lot of progress under these three pretty hard constraints, right? Positive examples only, and no feedback on if your guess is correct, and no active learning. Okay, very hard. And it's so hard, in fact, that Gold, in his very first paper, proved a theorem, a negative result that says there is no algorithm that can achieve language identification limit, even for incredibly simple collections like all regular languages. Okay, so you give me an algorithm, and I can build an adversary that will cause the algorithm to make infinitely many mistakes. And then Dana Englund came along in the late 1970s and characterized exactly the language collections for which an algorithm can perform identification. I should say, having primed this by pointing out that like this work steered us into the territory of computability, I was careful to say it steered us into the territory of computability style arguments, because this is not actually a result that's about computational computability, in the sense that these results, I can allow this algorithm to solve undecidable problems, have access to oracles for the halting problem. It doesn't really help, because as with impossibility results for online algorithms, the problem is not the hardness of the computation. The problem is that the algorithm simply doesn't know what the adversary is thinking of. The adversary is sending out these strings. The algorithm just doesn't know what the language K is. It can do all the computation at once, but the positive and negative results here, the somehow aesthetic of these questions, is the thing about the lack of information and not the hardness of computation. Okay, so negative results. And I said, okay, so that, I brought Sendel up to speed on Gold's theorem, and I'm like, this is why this whole plan is not going to work. And of course, it's also why you could say, Gold's theorem has been quite influential, but obviously people turn to probabilistic assumptions once they solve it. And yet, let's not give up quite yet, because this wasn't the question we were actually asking. Gold's theorem was the algorithm or the infant hears a bunch of strings, it has to guess the identity of the language. But that's not the problem we're asking the LLM to solve, and it's not actually the problem we're asking the 6-month-old to solve. Right? The 6-month-old grows up to become a fluent 6-year-old, and the 6-year-old speaks their native language fluently. But they're not going to be able to litigate edge cases of English grammar, for example, right? If you give them some complicated sentence and ask them, is this valid under the rules of English grammar, the 6-year-old won't necessarily know that. And frankly, a 25-year-old or a 50-year-old won't necessarily know that, right? We're not very good at it. In the same way that we learn to program in C or in Python, and we can generate valid programs, having seen a bunch of examples. But if we go to a really hard coding interview and someone asks us, would this double null pointer dereference compile successfully? We don't always know. We don't always know the corner cases of the language that we program in. So language identification involves patrolling the boundary, the exact boundary of the language. Generation just involves finding a safe space in the middle of the language that you feel like you can safely generate from and just keep doing that forever. That's all we're asking in generation. It's a very different activity. And so to our surprise, we went back to the lineage of work that Gold's theorem had touched off, and really no one had gone and asked, I guess because maybe generation wasn't as much in everybody's face at the time, or even in the decades after, no one had asked the question, what if we just change the Gold question to language generation? How would we do that? Okay, new game, very similar, still based on two-party communication. Adversary thinks of a secret language from a countable list. Adversary enumerates the strings. Let me add one more bit of notation for our new game. S sub t is the strings enumerated up to step t. That's the training data at step t. Okay, now the algorithm no longer needs to guess a language. It just has to, and this is the key line here, the algorithm must output a string, a sub t, that should come from the true language minus the sample it's seen so far. Right, that's the point. You should generate a valid string from k that has never been seen before. You can't just repeat what you've seen. And again, you have all the constraints that 6-month-olds have, no negative examples, no feedback if you're right or wrong. The languages are all infinite, because the worry is never that you're going to run out of things to generate, so that's not the issue. And the algorithm now wins in step, if there's some finite step such that after this finite step, everything it generates is a valid string from the language. Okay, so, and then we'll call this not identification in the limit as Gold did for his problem, we'll call this generation in the limit, different problem. Okay, so, all right, so Sun and I arrived at this definition. To our surprise, we couldn't then, find really anyone who had said what happens with this problem. And so we thought it'd be interesting to go back to Dana Engelwin's 1979 characterization of identification of the limit, where she gave a if and only if for when you could do this, and ask, is it the same, generation looks easier. Is it really easier? Is it actually the same characterization? Is it a more relaxed characterization? What is characterization? And for a little while, we were confounded by the fact that we couldn't find even a single instance where you could not do generation in the limit. That was kind of surprising to us. And so we puzzled over this. And the reason was because of a theorem that we eventually arrived at, which is that you can always do this. Okay, so here's the first theorem I want to tell you, that there's an algorithm with the property that for any countable collection of languages, and I mean literally any countable list of infinite subsets of the set of strings, and any enumeration, the algorithm will generate from k in the limit. Okay, so generation is always possible. The fact that you can generate from a collection tells you actually nothing about the collection. You can always do it, no matter how intractable this collection of languages is. Okay, so language generation is just a much, much easier problem. And this actually does mean, like, again, because the problem of outputting valid C programs is a completely mathematically well-defined problem, because C has a completely precisely specified grammar. And so yes, it really does say that there is an algorithm out there that if I just show it valid C programs after some finite time, it will output strings that are only valid C programs. Okay? All right. Obviously, like a result like this, because of Gold's theorem, we sort of know that a result like this is going to have to say, it's one of these results that we know from areas like computability, where the algorithm is going to win without ever knowing how it won. Right? There will come some time after which its strings are all valid, but it won't know what that time is, and it won't know what the language is it's actually generating from. We just know it will succeed at this particular task. Okay. All right. So, I mean, much like we sometimes puzzle at the fact that we regularly write programs in some programming language, despite not actually really knowing what the programming, like, there are programming languages that we happily write code in, and we don't actually really know the language. We don't know exactly what's allowed and what's not allowed, and it doesn't stop us from safely writing valid programs, right? And that's sort of what's happening here. Okay, so a few things. I want to show you a couple things. One, sort of the basic proof of this theorem, which is from the sort of original work that Sunderlei did. Then there's been a bunch of developments in this model in the sort of 9 months since we published this paper, and I wanted to show you how some of those developments have played out in the second half of the talk. A couple of points here. So obviously, a key point is that the algorithm only needs to generate from an infinite subset. So in some sense, if you're asked outside of this model, what is this telling us about language generation in practice, in real life? One is this tension between two kind of key concepts that I'll call validity and breadth. Right, like any approach to language generation is managing this tension between validity, that you should only generate valid strings, and breadth, that you have to go on forever, and so you must generate a large subset of this language. And the validity breadth trade-off really shows up in a lot of work on language generation, right? It's a balance between two extremes. At one extreme, failure of validity you can think of as hallucination, right? The idea that large language models hallucinate, they make up things that are not valid. At the other end is what generative AI people might call mode collapse, right? That you have this very rich set you could be generating from, but you've somehow collapsed down to this very thin subset, and that's all that you're willing to say, right? So you're not really exploring the full diversity of strings. And our algorithm is going to sort of look like that. It's going to start out by saying too much, saying invalid strings. It will continually sort of thin out the things it's willing to say. And eventually it's going to have thinned it out so much that it'll actually be safely contained within K. But of course, it's going to have to manage that thinning out all by itself because it never gets negative examples, right? So it has to somehow be in charge of its own sort of thinning out. Okay. One other thing I'll mention before I go on to proofs, there's another interesting thing going on here in the case of finite collections. And so I'll just have one slide digression about a theorem that we can prove for finite collections. Let me finally agree to the mean read transcribe, and then we can eliminate that. Finite collections. So suppose K is known to come from L1 to Ln. Now, N could be very large, right? I promise you that this has been produced by a grammar with at most K productions, right? There are a lot of grammars with most K productions, but it's finite. Now, Engelmann's characterization actually tells us that when it's finite, there actually is an algorithm for identification in the limit. So if there is, what more could we want? Like, what more do we want for our easier problem of generation? Well, one thing you don't get in identification is I can't give you an a priori bound T on how many steps the algorithm will need, right? I can't inspect the collection in advance and say, no matter how the adversary enumerates strings, I promise you that within T steps, I will have identified the language. Just looking at the collection, right? And a simple example is suppose my two languages were all strings and all even length strings. So I promised you that within 1 million steps, I will have identified which one it is. Well, then for the first million steps, the adversary shows me even length strings and asks me to make a guess. If I guess it's L2, all even length strings, then on the million and first step, it will show me an odd length string, and I'm wrong. And of course, if I guess that it's all strings, well, that's a terrible idea. I've only seen even length strings. Maybe it really is even length strings. So I can't give you an a priori bound. But for generation, you can actually. So another theorem that we can actually prove in this model is that for generation, if I give you any finite collection of languages, you can look at that finite collection before seeing the adversary and give me an a priori bound T based on the collection that says within T steps, no matter how the adversary enumerates strings, I promise you that I will have started successfully generating. So I can give this uniform time bound. And there's an interesting quantitative question here, which is this. The proof of this is partly constructive, but it leads to enormous bounds. And so there's interesting sort of quantitative questions going on with bounds that we might get. Okay, but let's, the techniques for this are really quite different. So let me go back to the basic theorem, the limiting theorem, which is in the limit, given a countable collection of languages, you want to be able to start generating after some finite time. How are we going to do that? Right, so you see some strings. So there's a bunch of intuition you can try building up around this, a bunch of dead ends actually, right? Like at first you think maybe there's some kind of like closure operation going on, right? So I imagine, change the scenery here. I say, I'm thinking of a secret convex set in the plane. I want you to guess what it is. And I put down some points. You're like, well, there sure are a lot of possible convex sets through those points. How could I possibly know? Which is a reasonable answer. What if I told you I want you to generate from my secret convex set? Well, then once I put down 2 points, you can safely generate from the line segment between them forever. Right, so there's some kind of closure operation going on, right? Well, what is it you did there? You said, I took the intersection of all convex sets that contain these two things, and I just discovered there were more points in that, and anything in that multi-way intersection is safe to generate from. So when you first look at these problems, you're like, maybe there's a closure operation going on. Maybe from the training data, the intersection of all languages that contain this training data also contains more things than I can generate from it. It turns out that actually works for the finite case. There really is a closure operation going on. There is a kind of convex hull being taken, which is kind of striking. But in the infinite case, I can very easily create examples where the set of languages that all contain the training data in my collection, if I intersect them all I get back is the training data. There is nothing else that you can be sure is safe to generate. So this kind of analogy to convex hull isn't quite the right thing. So with that in mind, you sort of turn to different ideas. And here's a totally different idea, which feels like it gets you very close, but then doesn't quite, at the very end, it fails. And so the question is like, how to make use of this idea, even though it's slightly wrong. Here's the idea. Let's really lean into the fact that this is, in the end, a countable collection of languages, right? And again, I promised a computability style argument. So let's start this enumerating our way through these languages, right? This is going to be a very slow algorithm, of course, but so be it. We're going to start with the hypothesis that the secret language is L1. And we're going to maintain this hypothesis as long as the train data is consistent with L1, right? I'll say the train data is consistent with the language of my collection if it's a subset of it. And so as long as our hypothesis holds, we're just going to keep outputting a string in L1 minus ST. And obviously we can do that because L1 is infinite. So we just keep searching for strings, higher and higher and higher until we crash into one that's in L1 that's not ST. And if we ever get to a step where the train data proves our hypothesis wrong, we just move on to L2 being K. And we just do that. And you almost feel like you can see a proof that this will lead to generation of the limit, right? Here's a proof that turns out to be actually not just wrong, but really fundamentally wrong, that if I'm currently hypothesizing L sub I, but it's not the right answer, then eventually I will discover that from the enumeration of K, and I'll move on to Li plus 1. And of course, the true language is LZ for some index Z. It's just sitting out there somewhere. And so I will just eventually methodically get to it. And once I get to it, I'll never move on because it's the correct language. Right, so it has all the ingredients that we sort of thought a solution would need, which is I'm winning without ever knowing when I've won or how I don't know when I get to LZ that I'll never move on. It just so happens, happily, that I never do move on. Okay, so that's what at first looks kind of like a proof. Like, okay, so doesn't this just work? But there's a big problem with this proof. The problem is that before I get to LZ, there could be an earlier language that's a proper superset of it. And I see only positive examples, right? Because we're under this 6-month-old language learning constraint. And so I hit L sub I, a proper superset, and I never move on from that. Because I only see things that are consistent with, I could hit Li could be the set of all possible strings. Surely that's a good hypothesis. It contains, it'll always contain the train data. So I'll never move on. And in some sense, so you can say, maybe if we just think about this a little bit differently, we can make this go away. But we can't make this problem go away. Because in a way, if we can make this problem go away, we could also solve identification in the limit. There's nothing I told you in this proof sketch that was specific to generation. I could have solved identification this way also. So this is actually sort of deeply wrong at some level. But it's also worrisome, because if you think about, okay, intuitively, how are we going to solve this problem? Using this strategy. Like, we're going to try to make the strategy work. But to get the strategy to work, you're faced with the following dilemma. You get to language L sub I. You sit there for a while. Training data comes in. It's all consistent with Li. It looks great. You have two choices. You can say, well, things look safe here. Let's just stay here. But we know that's a bad idea, because this might be too big a language, and you'll be wrong forever. So you have to move on. But if you move on, that means you're going to move on even when you're at LZ, the true language, which was your one stopping condition in this whole thing. And so if you move on beyond LZ, now you're just drifting out to C forever. Like, there's nothing to stop you. Right? Like, what are you going to anchor on if you're beyond the language LZ? Okay. So that's the issue that we have to get around. Just to kind of draw this picture in a little more kind of eloquently. Right? We can imagine each language is like a bit vector showing, like, L1 has string 1 and string 3 and 5 and 7 and so forth. This one has 1 and 5, and L3 is the infamous language that has everything. And the adversary shows us things like U12 rules out nothing in the first 7. U9 actually rules out L1 because it's not in there, but it keeps the rest, and so forth. Looking at a picture like this, we of course appreciate that obviously if Li is a subset of Lj, I'd rather be generating from Li than from Lj. I'm always trying to generate from smaller languages. That's strictly safer. So it'd be nice to find some kind of like a minimal language, but these are a countable list of infinite languages. There may not be any minimal language. I could have just these big infinite descending chains of thinner and thinner, but still infinite languages. And so there is no like minimal language. Okay, so what do we do about that? So it'd be nice to get minimality to work. Minimality isn't going to work over countable collections. Is there some finite collection I could get minimality to work over? And one idea, and in some sense, like once you try this idea, everything just starts working, is let's think about things that are like a language L sub n, which doesn't have to be minimal over the whole collection. That's an infinite collection. It only has to be minimal over the things that have led up to it. So L sub n, a consistent language that is sort of very thin in the sense that if you look back to its left, back to the earlier languages, it's a subset of all the earlier consistent languages. Let's call that language, such a language, critical. Okay, so L sub n, and this is actually sort of the key definition to get this to work. L sub n is critical at step t if two things. One, it's consistent at step t. And two, for any earlier consistent language, Ln is a subset of it. Okay, so all the earlier ones are bigger. And again, I'll sloppily use words like bigger and smaller. These all have countable cardinality, but I mean superset, subset. Okay. Here are two facts. First of all, there always is at least one critical language. Like think of at any time t. Think about the lowest indexed consistent language. That must be critical because nothing to its left is consistent, so it's surely a subset of all of them. Second, and more importantly, the true language will eventually become critical. Right? It may not be critical right away. Like here in our little example, it's not critical because L4 is not, it's not a subset of L4. But that'll change once U5 shows up because that'll rule out L4. So in other words, for every earlier language that LZ is not a subset of, it means that LZ has something that that language does not. Right? There's some string that's in LZ that's not in that earlier language. That string will eventually show up. And so if we just take the max of all those times, that's a time by which a witness has shown up to rule out every language before LZ that is not a subset of. And at that point, which we don't know when that'll happen, but by that time t plus, it will actually be critical. Okay, why is it useful to have critical languages? Well, once you have critical languages, it's not hard to kind of leap to an actual algorithm for generation in the limit. Here is the algorithm. So again, another computability style argument. In step t, we're going to maintain this widening window such that we're only going to consider languages L1 to LT in step t. Right? So the window will widen, but we're only going to look at finitely many languages in any given time step. And among all those languages, let's say L sub NT is the rightmost critical language. It's one with the highest index above t. And the algorithm is simply generate a new string from L and T. Okay, find the rightmost critical language, generate a new string from it. I want to claim that algorithm achieves generation in the limit. Why is that? Well, let's run time forward, right? Of course, the nice thing with generation in the limit is you can be wrong as often as you want, as long as you're eventually right. So let's be wrong for a whole bunch of steps, but consider step t star, where t is big enough that first of all, it's bigger than z, which means in our window of L1 to LT, LZ is included. It's a candidate. And second, it's bigger than this bound t plus, which was the time after which LZ was going to become critical. After this point, well, we have this list of, somewhere in L1 to LT is a bunch of critical languages. LZ is one of them. And we picked the last one. So the last one comes after LZ. And by the definition of criticality, this last one is a subset of LZ. Right? Because the critical languages form this descending tube that goes to the right. Right? Thinner and thinner languages moving off to the right. And L sub NT is the thinnest of all of them. And it comes after LZ. So any string that we output from LNT also comes from LZ. And that's the whole algorithm, right? So it again has this property that we've won without ever quite knowing how we won, right? Like we're traveling down this list of critical languages, thinner and thinner subsets. Never quite sure whether we've succeeded yet, but we know that eventually we're going to pass by LZ and we will have succeeded, right? A few observations here, and then I'll tell you about some of the new things that we've been doing. So first of all, the algorithm is actually achieving something a bit stronger than the original. The original requirement was in step t, it has to output the string a sub t, which comes from the language. But it's actually doing a bit more because it's doing what you might call index-based generation, which is In step T, it's actually outputting an index, IT for the language, in the style of Gold's theorem, with the property that the thing it outputted is a subset of K. Like, if you can do this, you can do that. Because if I know I have a subset, I can just generate anything I want from this, and it will be from the true language. So index-based generation is stronger than element-based generation. This algorithm is actually showing that both things are actually achievable. I would also point out, like, both things have a meaning in the context of actual LLM design, right? Like, obviously the LLM is, from a kind of user interface point of view, showing you strings. It's outputting sentences. But from an internals point of view, the training has actually produced some representation of the language, right? So if I think of these indices, I1, I2, I3, as basically shorthand for architectures, right? There's a countable number of possible architectures that the LLM could be using, clearly because they're all finite. And so it's just iterating over possible architecture. And it says at the time t, it has an architecture that generates a subset of language. Okay. So in some sense, both index-based and element-based generation have some natural sort of meaning that you can locate in the actual way these things are being built. And they're sort of arguing that this algorithm is doing some kind of extreme form of regularization in that it keeps restricting, right? It keeps finding more and more restrictive architectures such that eventually is safe to proceed. Actually, a couple of other footnotes here, and then I'll move on to some of the new things. So a couple other footnotes. One of the footnotes is, so as I said, the aesthetic around Gold's theorem is that we're not really worried about computability. We're worried about this problem of sort of guessing what the adversary had in mind, even if we do non-computable things. And true to that, this algorithm actually does something non-computable, which is it decides if the language is critical, which involves solving a subset query on a pair of languages, which we can't actually do with a finite number of membership queries. Now, that was never really the issue with these Angevin-Gold style impossibility results, but of course, it'd be nicer if we could give an actual algorithm whose computational steps consist only of membership queries. And the answer is you actually can do that using one more trick that I won't get into. But essentially, remember that our algorithm was working with a wider and wider window of L1 to LT. That's kind of like widening the window this way. Let's also widen the window this way. So in step T, we're only going to look at prefixes of the languages that go from string 1 up to string m sub t for some value m sub t. And then I just widen, so that's the orange bars here. And I just increase m sub t as I go. And I change all the definitions to get that to work, right? So we have to sort of take the one elegant thing we had going on, which was the definition of critical, and sort of blow that up. So we have now this much messier notion of like, it's critical, but only over the prefix that we're working with. But eventually the prefix that's big enough that that's going to be okay. So a messier algorithm, but one that only works with membership queries. The other footnote, before I move on to more recent things, this was all without prompts, right? You could say like, there's a missing part of our lived experience with LLMs from this whole story, which is we prompt it. We don't just say, output a C program. Right? Like we say, I've started the skeleton of my C program, please finish it for me, right? We prompted it with something. And so, but once we have this algorithm, it turns out the algorithm is sort of rich enough that it can also handle what you might call prompted generation. Okay, so here's what prompted generation is. We're going to interleave, just for convenience, essentially the training and the prompting. So we'll say in every step, the adversary shows a new string of k, that's part of the training, and also a prompt that it would like the algorithm to complete. And then the algorithm must return a valid completion. In other words, a string, so it shows a prompt pt, the algorithm replies with a completion c sub t, so that the concatenation of them is a valid string. Okay. So far, we've basically been talking about prompted generation with the empty string, right? I keep prompting with the empty string and say just fill in anything. But you might want to show it a real prompt. And basically, an extension of our algorithm achieves prompted generation in the limit. You still find the last critical language, you see the prompt, you just work your way up L sub nt till you get to something that completes the prompt. And we'll make the assumption here, right? So that basically works in the case where every prompt has an infinite set of valid completions. All right. I want to get on to some of the things we've been. So a question that I think was sort of very interesting in all of this, if you pop back up, is the tension between validity and breadth, right? Like in some sense, although this model is extremely abstract, one question that I would argue it puts on the agenda for large language models is how do we really think about breadth? Like, how do we think about the fact that ultimately these models are succeeding by picking some very restricted set of language that they're willing to generate? And we have very little understanding of how restricted that is, right? Like the question of, is Claude, Gemini, or ChatGPT willing to say dramatically more things than the other two models is not a question we actually know how to answer, right? That might be true. It might well be true that one of those three models is just much, much more expressive than the other two. And we just don't have good benchmarks for even measuring that because we don't have a good way to formalize that, right? That's the breadth problem. And so one hope here is that a model this abstract can let us sort of think about breadth as an object in itself so that we might be able to finally get back to answering questions like that that actually apply to real language models. And so there's been a bunch of follow-up work, including some that I've been doing with Fan Wei that I'll be talking about, also nicely summarized in a Colt 2025 tutorial that a group of these authors put together with some nice videos online, which kind of summarizes the state of thinking about validity and breadth in this model. The particular take on breadth I want to talk about was via density, right? So density of subsets of the natural numbers is something we're kind of familiar with, right? So we know that the primes have asymptotic density 1/log n in the natural numbers. I mean density in that kind of sense, right? So if I think about the true language k, I could say f of n is the fraction of the first n strings of k that the algorithm eventually outputs, right? Like if we run this algorithm forever, then each string either eventually shows up in the algorithm's output or it doesn't. And so let's look at all the ones that do eventually show up. And let's look at f of n as the fraction of the first n strings in the output. And then we could ask about its density its limiting density in the true language. How much of the true language, this is the best way I can of expressing the question, how much of the true language is being expressed by this model? Does it express a lot or does it only express a little? Is it very restricted or is it very expressive? Now, the lim in for this thing might not be the same as the lim sup, right? I mean, these numbers bounce all over the place as you work your way up through the language. And so those might be different. So we should talk about the upper density and the lower density. Obviously, it's easier to achieve a big upper density. Now, the algorithm we've seen so far it's particularly interesting to consider this because it can easily produce solutions that have upper density 0. It's succeeding, but succeeding by mode collapsing onto an arbitrarily thin subset of the language, right? These critical sets just get thinner and thinner as you move out to the right. Right? It's sort of collapsing its way through hallucination. There's a moment when it has the right solution, but it keeps going and it just collapses, right? In a way, there's sort of an interesting parallel to some work that my colleague Cristian Niculescu-Miesel did in a totally different context, where he was studying how people acquire the vernacular in a new online community, right? So you join a new subreddit and you're posting, and people have all this like slang, this inside terminology that you're not really familiar with. And at first you misuse the slang, right? It all sounds wrong, right? You sound like a newcomer. Gradually, and this is what actually happens in his data, you learn the slang, you actually sound like a regular in the subreddit. You actually use all the terminology correctly and everything. But of course, the world evolves. People make up new slang, new shorthand, new abbreviations, whatever. And what you find is that Reddit users don't adapt. They stick to the language as they finally learned it when they arrived. They got good at that, and they don't. So in some sense, they age the way people age linguistically, right? That old people just can't pick up the slang the teenagers use. That's happening at high speed in these online communities. And it's also weirdly happening here. The algorithm somehow starts out saying too much and sounding wrong. There's a moment when it actually has everything right, but of its own volition, it just keeps becoming more and more rigid in what it's willing to say. And so there's this question, must every solution to language generation limit have something like this structure? And fortunately, I did not write down a conjecture about this in our first paper on this because my conjecture would have been wrong because the answer is much more subtle than I thought. It sort of felt like, surely this must be the way to solve the problem. So maybe there's a theorem that says, yes, there are always instances where you can do this, but only at 0 density. It turns out that's not true. So in a paper that's appearing at Fox in December, what Fan Wei and I can show is there's actually an absolute constant C and an algorithm that achieves generation of the limit whose output always has lower density, at least C, this positive constant C, which we can get as high as 1/8 is the best we can do. There's a lot of evidence you can probably do better. You can't do better than 1/2 for reasons that are reasonably simple, which I won't go into in the interest of time. But I want to tell you a bit about like how we prove this. Because in order to prove this, we're going to need actually a dramatically better algorithm for generation in the limit. Right? The algorithm we have for generation in the limit so far has the advantage of I can explain it to you in real time as I just did, but it's very wasteful, right? It throws away huge amounts of the language in order to succeed. We're gonna have to throw away a lot less of the language if we want to achieve a result like this. Now, to get there, it turns out it's useful to go via index-based generation. So index-based generation, remember, is the algorithm is guessing indices, and you eventually want to be a subset of K forever. That's what index-based generation means. So let's think about an index-based generation algorithm. And let's say D sub T is the upper density of its guess in the true language. What can we say about this sequence of densities? Okay, so we're now talking about basically the lim sup of a sequence of lim sups, right? So it's a little indirect because each of these densities is some limit, but we want to talk about the sequence of densities over its guesses. Okay, what can we say about that? Well, so first, there is a hint of a negative result here, right? Even though the eventual result is positive, this is actually a sort of even more dire question. It's saying, like, can you guarantee that every guess you ever make of what the language is always has positive density in the true language? That's asking for more than just that the eventual output has positive density. And that you actually can't do. So just to take a simple example, let's consider like the following instance. L0 is the set of all finite sets of positive integers, and Lk is the set of all size k sets of positive integers. Okay, so the set of all finite sets of positive integers is some countable list. I could canonically order it in order of increasing sum. Here are the singletons in black. Here are the 2-element sets in red. Here are the 3-element sets in blue. I just keep folding them in. Now the problem is an adversary can simply show you a bunch of singletons until you get, like, at some point you're going to have to guess, because remember, index-based generation makes you guess the identity of a language. Eventually you're going to have to guess that the true language is L1, because that's all you've seen. It waits until you've done that. Like, you have to do that eventually or you're going to be wrong infinitely often. As soon as it does that, it starts showing you 2-element sets, and then you guess it's L2. And you do that for a while, and then it shows you 3-element sets. So, and of course, the answer will be that it's L0. And that's fine from a generation point of view. It's been a subset of L0 the whole time, so no problem on correctness. But the problem is each of the LKs has 0 density in L0. And so you're going along 0 density sets this whole time, right? And so in some sense, like, we can actually characterize when this happens. It happens when you have a structure exactly like this, a sequence of expanding sets that eventually union out to the true answer, where each of the sets in the union has 0 density in the final answer, right? So essentially a sequence of sets that sneaks up on the answer, right? The union is the whole thing, but it has 0 density all the way along. And that's actually, when that happens, the adversary can play the strategy. But it's actually, it's a bidirectional implication. It's an if and only. On the other hand, so that's a negative result. But you sort of notice that, like, every time the adversary switches from L2 to L3, L3 to L4, the algorithm realizes the guess has changed, and it can spend some time outputting some more stuff. So this doesn't actually stop it from outputting strings. It just makes its guesses a bit random. So that actually gives us the first positive result. And I'll sort of hint at this, and then I'll start wrapping up. That was that infinitely often you have to say 0 density things. But an algorithm isn't condemned to only say 0 density things. Consider the algorithm here that every time it changes its guess, it says L0 once. Right? So when it goes from L1 to L2 as its guess, it actually says L1, then it says L0, then it goes to L2. And when it has to change from L2 to L3, it says L0, then it says L3. Okay? That algorithm is actually right infinitely often. And that was the surprise to us. Right? The surprising positive result that sort of kicked off all of this is that, let's say an index-based generation algorithm is accurate in step T if it happens to have the exact right answer in step T. Now, Gold's theorem says you can't be accurate forever. You're going to intersperse infinitely many mistakes. But the surprise is that there's an algorithm that achieves index-based generation in the limit that's accurate in an infinite sequence of time steps. Okay, so infinitely often you actually have the right answer. This was a thing that I had thought you could not do. And the reason I thought you couldn't do it is because the whole premise of this working is that you're going out to the right? You're not sure where LZ is. So you keep having to move right through critical languages. Like, what else can you do? And to do this, you're going to have to also have another process that moves you back to the left, right? Trying to make your way back toward the bigger language. But that's very dangerous, because if you keep moving back to the left infinitely often, then you're going to overshoot, right? Aren't you going to like end up at a too big a language infinitely often? And you'll make infinitely many mistakes. How is it that you can come back infinitely often and every single time just get to here and no further, right? Like, what's going on there? Yet, to my surprise, that turned out to be possible. And I can't really tell you exactly how this works in the time I have, but the basic idea is that there's an extra thing going on that's super useful, which is when we're doing generation, if the string I see is in all of my critical languages, I should do what I was doing before. Just keep this wide window and output from the rightmost one that you see. But when the string I see is not in every critical language, there's a rightmost one it's in, which actually destroys all these critical languages. And that gives me a moment in which I can output from this one. I can guess this one. Okay? So think about that algorithm. So I have this infinite chain of critical languages, but I'm not condemned to just move monotonically to the right down it. Because there are these moments when critical languages get destroyed. Because if they're a proper subset of this one, there's something here that's not here. And so that will eventually show up. And that doesn't just destroy this language, it destroys everything out there. Right? So the set of critical languages is this sort of organic object that generates these infinitely long threads. And then every now and then you snip the infinitely long thread and a new infinitely long thread grows. And then you snip that one and a different one grows. And every time the snipping happens, that gives you a moment to jump back and guess this language. Because there are two possibilities. Either this one is right, in which case, great, or it's wrong, which is fine. It's just one of your finitely made mistakes, because we know the string is going to start growing again. Okay? And in particular, the critical language that at the moment comes right after K is missing something. So eventually that will show up, and that gives you your chance to guess K. So infinitely often, you'll be able to guess K, because at every given time, there'll be some next critical language after you. It's missing something, which will show up, and that lets you guess K. And so infinitely often, you're right, and you generate, right? So you're staying to the right of K, so you're generating the limit. And infinitely often, you make it back to exactly K. And so that actually lets us get positive upper density of a half pretty easily. Because I just keep guessing these languages, and every time I guess a language, I generate many, many strings from it, which allows me to push up the upper density. The lower density is just much, much harder. And I'm gonna jump over that, I think, in the interest of time. How much time do we have? Like, wrap up now? Good time to wrap up?
Yeah, that's probably.
Yeah. So that brings me to the end. The idea was start from this very simple spec, right? Like start from one sentence, which is, let's throw away all the probabilistic formalism that we typically think of associated with LLMs and go back to a purely deterministic sentence, design an algorithm that produces strings from an unknown language, and eventually begins producing valid strings that have never been seen before. The only, clearly, simplicity is an appeal of this sentence. The problem is it seems to be asking for too much. And somehow this whole project got started with the surprise that it was not asking for too much, that it really is possible to meet the spec in a very concrete way. And then I think what's been interesting is how it sort of really calls into sharp relief this tension between validity and breadth. Right? Validity we understand arguably better. We know how to evaluate output by output. But breadth is this elusive thing, right? That even for real LLMs, I don't really know how to talk about the breadth of what it generates. And so this is sort of letting us talk about this. The initial algorithms sort of are kind of really profligate in how they throw away breadth for the sake of correctness. But these more recent algorithms that we've been working on are much more careful, right? And they try to work both sort of forward and backward through the list of languages to try actually maintaining positive density. And so I think this leaves us, first of all, with there are a bunch of interesting open questions about how tight can we get these bounds on density? What are alternatives to density as measures of breadth? But it also leaves us with even a question I think is very important to formalize, even down in the world of Claude, Gemini, ChatGPT, and DeepSeek, to ask, how do we really measure breadth in a real deployed LLM, right? If I'm working with two LLMs and one actually deep down has much better breadth than the other one, how could I possibly elicit that or measure that? That's going to require some kind of formalism that we can quantify. And I think for all of this, it's going to lead to a very interesting set of interactions going forward. And one that, again, I think sort of really productively centers a theme that was has been present in so much of Mark's work of really centering communication between multiple parties as a really powerful formalism, even for problems that initially on the surface don't seem like they have much to do with it. So I'll stop there. Thanks very much.